So today's video is going to cover pedigrees. And I'm going to have you guys just follow along on your handout and get this down, and this will act as your notes. Okay, so we'll point certain things out and we'll do some examples, and then you will use this as a reference as we do other problems in class. So, a little background on what a pedigree is. So, a pedigree tells us basically how often a trait occurs in a given family. And so, by looking through the pedigree, we can start to see how things are transmitted through the pedigree. So when we're reading a pedigree, we need to realize that squares are always going to be males. Circles will always be females. When the shape, the circle or the the square is shaded in, then that shows that that person has the trait. So for example, this right here is a male that has the trait, where the circle is a female that does not show or express the trait. Okay, a line connecting the two shows that they are married. This line coming down from that shows that they have had children. So these are all the children. Okay, and so these are all siblings here. If there is a line between that linkage there, that shows they are divorced. If there is a line that goes through the shape itself, it shows that that person has died. Okay, so we have three basic types of pedigrees. So really your expectations are going to be, you're going to be given a pedigree, and then the expectation will be that you can determine what kind of pedigree it is. And then from there, you can do genotypes and Punnett squares from it if you needed to. So we have three basic types of pedigrees: autosomal dominant, autosomal recessive, and sex-linked recessive. So when we're looking at a picture of a pedigree, so a pedigree is going to, look something like this. Maybe they get married and they have a child, and this one gets married and they have two children. So pedigree looks something like that. So when I'm looking at a pedigree, I can tell that it's an autosomal dominant trait if it appears in every generation. So each line here is a generation, and they're written in Roman numerals. So each line here is a generation. So the trait shows up in every generation. So somebody would be shaded in every generation. At least one person would be shaded in every generation. And every person that's affected with the trait is going to have at least one parent that's affected with the trait. Okay, so that's what we're looking for when we look at an autosomal dominant pedigree. It's in every generation, and everybody that has it has at least one parent that has it. For autosomal recessive, I need to realize that I could have people that have the trait, but their parents are normal. Okay, so basically what it's saying is that it can skip generations. So for instance, I can have somebody here who has the trait. So this person here in generation 3 who has the trait, but the parents are normal, because if it's recessive, right, the parents could not show the trait, but they both could pass it on if they were carriers. And then for sex-linked recessive, what I'm going to look for is that the trait is most commonly occurring in males. So lots more of my squares are shaded, not just like one or two. Lots more of my squares are shaded. And then a female only has it if her father has it. Remember, females, to get a sex-linked recessive trait, have to have the recessive allele on both X chromosomes, meaning the one that came from her father would have to contain it. All right, so we're going to look through some examples of these and kind of see what problems would look like regarding these. Okay, so looking at this one here. So remember this is an autosomal dominant pedigree. And I know this because every generation has at least one person with it. So every generation has at least one person with it. And I know this because everyone that has it has at least one parent that has it. So it didn't skip generations. I don't have carrier situations happening here. Okay, so one of the things I need to keep in mind here, remember, shaded people are the one that are expressing or showing this trait. And this, again, is a dominant trait. So everybody that's not shaded doesn't have the trait. So they're going to be homozygous recessive, right? If my 3 genotypes are homozygous dominant, heterozygous, and homozygous recessive, if this is a dominant trait, this person doesn't have it. This person has it. This person has it. So all the unshaded people that don't have the trait, they're homozygous recessive. And then we know that everybody that is shaded is going to have at least one dominant, right? Because all it takes, this isn't an incomplete, this isn't a codominance, right? This is normal dominant. So all it takes is at least one dominant to win. From there, I need to decide if they are either unknown or if they are heterozygous. Okay. What I never, ever, ever write in a pedigree is that I know for a fact that they're homozygous dominant. And we can talk in class about why that is if you want to. Okay. But what we write in a pedigree, if we know for sure they're heterozygous, we can write that. If we don't know for sure that they're heterozygous, we write a question mark. So let's see how we can figure that out. So this first person right here, this person in generation number 1, you see it numbered over there, generation 1, individual number 2, this person right here. Okay, if I look, I don't know any information about their parents, but I do know information about their kids. And they have kids that are little a, little a. They have kids that are homozygous recessive. So what that tells me is that they had to have a little a to pass on to their kid. So now I go to generation 2, individual number 1. I go to this guy over here on the end, on the far left. Well, he doesn't have any kids. But if I go backwards to his mom is little a, little a. So the only thing his mom could have passed on to him is a little a. So let's hop over here to this end, to his sister here. She has a child that is little a, and her mom is little a, little a. So we know she has to have that to pass on. Her son, okay, her husband is little a, so that's the only thing he could have passed on to the son. It's the only thing he could have passed on to the daughter. But now I have this chunk of family right here. These children don't have any children of their own, and both of their parents are expressing the trait. I cannot assume that this dad over here is big A, big A. I have to write that I don't know. Because when these kids have their own kids, maybe they'll have some kids that show up as homozygous recessive. Okay, so I can't definitively write down big A for any of them. I write down big A question mark. Okay, so remember when it says which individuals are female, we list the individuals by the generation. So for instance, generation 1, individual 1, that's a female. Generation 2, individual 2, generation 2, individual 3, and we would keep going. All the circles are females, right? All the squares are males. So for instance, generation 1, individual 2, generation 2, individual 2. I'm sorry, I messed this up here. This is 3 and 4 for the females there. Generation 2, individual 1, and so on. All the squares, right? Circles are females, squares are male. We already did number 3. We wrote the genotypes all over. Some individuals I can't find the genotype for because I don't know their parents, or I don't know if they will end up having more kids that will express the trait. I just don't know. Okay? And so now we get into these relationships, and we can look at these a little bit. We won't spend too much time here. But for instance, the relationship between the individual 3, 4, so generation 3, individual number 4. So that's this gentleman right here. And then generation 3, individual number 1. So over here. Okay, so if we trace this, they're in the same generation, so they could be brothers, but they don't have the same parents, but what they are brother-in-law, right? They're married. The one guy is married to the other guy's sister. All right, generation 4, individual number 2, so this girl right here. Generation 3, individual number 1. So the same guy right here. Okay, well, she is his sister's child, right? So that is going to be a niece to uncle situation. Okay, so let's jump down to number 8, where it says, what is the probability of, hold on, let me clean this up just a hair here. So it says here, what is the probability of 1 and 2, 4 and 2, 5 having another child with the disorder? Well, that's a Punnett square situation, right? So I'm just going to go look at those two individuals, which I just erased. Right, so sorry, cleaning up just a touch here. Okay, so if I go look at these two individuals, 2, 4, which is big A, little a, and 2, 5, which was little a. So Punnett square. And again, I have to keep in mind that this was a dominant trait, right? So the probability of them having another child with the disorder is this one and this one. So 2 out of 4 or 0.25. All right, let's look at our next one. So our next one is for autosomal recessive, not sex-linked recessive, but autosomal recessive. So the same rules apply. The shaded people are the one that express the trait, but this time it's a recessive trait. So if I'm going to show a recessive trait, I have to be recessive, right? I have to be homozygous recessive if I'm going to show a recessive trait. So anybody that is shaded is homozygous recessive. So again, then I know that everybody that's not shaded has at least one big A. And I can go through and I can use the same logic I did before by looking at the parents and the children to determine if they're little a, if they're heterozygous, or if they are unknown. Remember, unknown, we don't write big A, big A. So I have this first female here. She has a child that was little a. So I know that she has to have a little a to pass on. Okay, I have, when I look at her children here, there's a daughter here. The daughter's child doesn't show the trait. However, the dad, the daughter's father, had the trait. So she had to get a little a from him. If I look at her husband, we don't know anything about his parents, and their child, we don't know. So we cannot confirm that they're going to be big A, big A. We don't know. They could show up to be heterozygous. This couple right here could go and have 4 more children, and the next 3 all have the trait, and then we'd know for sure, right? But right now, we just don't know. So looking at individual 2, 4, so this female right here, again, her father was little a, so that was the only thing they could pass on. Same for the brother. The father had to have passed on his little a. So now we look at the wife. Okay, the wife, she's not an unknown. They have a child that's little a. So because that means she had to give a little a. So again, we look at the parents and the children to determine if they're heterozygous. And if we can't for sure determine if they're heterozygous, we just put a question mark. So we already did number 1. We do a couple of relationships here, individual 2 and 3. So this one and this one, they are sister and brother. Individuals 2, 5 and 2, 6. So this one and this one, they are husband and wife. Okay, so let's jump down to number 6. Individual 2, 3. So this one right here, individual 2, 3 marries a heterozygous woman. What are the chances of having a homozygous recessive offspring? So again, I Punnett square this out. And their chances of having a homozygous recessive offspring are 2 out of 4. 1/2, 50%, 0.5. Okay, so let's look at our last pedigree here. So our last pedigree here is for sex-linked recessive genotypes. So I need to be thinking as soon as it said sex-linked that I'm going to have to do those X's and Y's. Okay, and so let's go ahead and just do that first, right? Females are circles, so males are squares. So let's go ahead and XX and XY, all these males and females. And then I need to remember that sex-linked recessive traits are carried on the X chromosomes only, not on the Y chromosomes. So when I'm putting in information about a sex-linked trait, Okay, I'm only going to put it in on the Y, on the X chromosome. So let's start with the males. So for instance, the individual 1, 2, the first generation, that male there, does not express the trait because he's not shaded. So he's got to have dominant. Individual 2, 1, again, not shaded, doesn't express the trait. But his son does express the trait. So he has to have recessive. Individual 2, 3, this male in the middle here, not shaded, doesn't have the trait. Shaded expresses the trait, so has to be recessive. Same with his brother, individual 2, 5. In 3, 5, that individual, that male expresses the trait, so he has to have the recessive allele. Same with his son in generation 4, individual number 2. So now we go back and look at the females. If we have a shaded female, we know that she has to be homozygous recessive. Remember, that female is going to have the trait, right? They're going to have or express it. They also, females could also be heterozygous or carriers, so they would not express it, but they could pass it on. And then in a pedigree, they could be unknown, because remember, we don't write big H, big H. So starting with this first one here, okay, if I have this first female here, I know she has at least one big H because she doesn't express the trait, but she has a son that does express the trait. Well, the son got his X from the mom, so she has to be little h. Same with his brother here, which is where he got his little h from. The mom, because the dad is who passes on the Y to the males. Okay, so now let's look at generation 2, individual number 2. Okay, her dad, she's dominant. We know that. Okay, she has a son that has it. So she had to have a little h to pass on to that son, right? Because he got his Y from the dad. Her daughters don't have it. So we know that they have at least one dominant. But what we don't know is, yes, we know that dad had to give them an X big H. We know that. But mom could give a big H or a little h, and it wouldn't affect what they looked like, right? Mom could give them either one, and it wouldn't affect what they look like. So these two daughters here are unknown. We don't know what they would be. Okay, so let's look then at a couple of these last few females here. So the mom, well, we got the mom there. Let's go to the far right, generation 2, individual number 6. She doesn't express it, so she's big H, but she has a son that does express it. So she had to have a little h to give him because, again, he got the Y from dad. That son's wife is big H. She does not express it, but again, she has a son that does. Okay, and then her daughter doesn't express it, so she's big H, but she has a dad that has it. So that dad had to give her the little h. So we can tell what she is. She's not unknown. When I see this pedigree, I know this is a sex-linked trait because, again, lots of males, 1, 2, 3, 4, 5 males compared to 1 female. So not like 5 males and 4 females, right? Lots of males. And then the female that does have it, her father has it, right? The female that does have it, her father has it. So you'll need to be able to determine when you get a pedigree, is it autosomal dominant, autosomal recessive, or sex-linked recessive? So that's looking at those rules. Is it in every generation? Everybody that has it, do they have at least one parent that has it? Okay, autosomal dominant. It skips generations. I have people that have it and their parents don't have it. Okay, it's autosomal recessive. I have lots of males that have it, very few of any females. And if I do have a female, her dad has it. Okay, I need to be thinking sex-linked. Okay, so we're going to jump straight down to number 6. What is the probability of individual 2, 1, and 2, 2 having a boy who is affected? So 2, 1 is this unaffected male, and 2, 2 is this carrier female. So I am looking at the probability that they have a male or a boy who is affected. So that is 1/4. Probability of a boy is 1/2. Probability that they're affected is 1/2. I want those to happen at the same time. 1/2 times 1/2 is 1/4. And probability of having a girl that is affected is 0. They don't have any girls that are going to be homozygous recessive. Okay, so we'll do some practice with these in class, identifying them and then answering genetics questions.